the outset, let me thank the Indian Academy of Science for the honor and the opportunity to briefly speak here on certain aspects of what we do. This is what I'm going to talk about today. So before I forget, I usually probably will run out of time, or I'll tend to forget. So let me just acknowledge the several people who are involved in the what that I am going to present. Across the different parts of the globe, but primarily the work is done by this PhD student Ravindra Yadav, who just graduated earlier a month back. Okay, so I'm not going to talk about some of these things, but I thought I'll briefly just show the other activities that our group is involved in. Primarily, two aspects involved in soft and biological physics, as well as sort of the other things that we do, which I'm not going to talk about, including different materials, 2D materials, and a lot of other systems. So what I'm going to talk about today are two kind of more recent things that we have studied using this quantum emitter, which we have, of course, working on for quite some time. I showed in the previous slide, but now coupled to different types of what are called plasmonic and one which basically allows range of Polariton energy transfer, and the other one which involves observation or emergence of photon spin momentum locking, and I'll explain this as I go along. So first of all, plasmonic lattice. This is a lattice. I think we are all familiar that you have an array of some entities. We know about solids, atomic crystals, where you have this lattice, but unlike the atomic crystals, what you have here are more like crystals which are in the optical regime. That means as this SEM image scanning microscope shows, this is a lattice which is the dimension you can see from the scale bar here is something of the order of 200 nanometer, and this can be tuned to vary go to even a longer length scale. But so this is something that I'm referring to, and there will be one more type I'll come to in the next slide. So, but basically, what is interesting about this? So, of course, these are made of. You can make this of any type of entities. It could be dielectric, it could be metal, it could be any other type of material. But essentially, what is interesting is that you actually can. So here I'm showing this in the metal particle. What will happen is each of these will have, or they have something called a plasmon resonance, which is kind of the collective oscillation of free electrons in these materials, which is metal. But apart from that, when you put them in this array, you end up with this type of a very sharp mode. So the resonance, this is transmission as a function of energy. So this is usually what people measure as the optical transmission, or in absorbance will be a peak for an individual one. But when you put them in this type of a regular array, then you end up with this particular mode, which is, as you can see, much sharper and very very kind of well defined. And this also you can tune, right? The other type that I'm going to talk about is the so-called hyperbolic metamaterial, which is a type of a metamaterial where I'm showing an image here, for example, where you can see again nice sort of an array. This is an hexagonal array, except that the dimensions are smaller. They are considerably smaller, something around of the order of 100 nanometer or less. So they are sub-diffraction, okay, and therefore you will not see the feature that I showed in the previous slide. But what you end up is that you can define this at the optical wavelength. For this is something which is sub wavelength. You can treat them in terms of an effective medium model. and come up with some sort of a phase diagram shown here, where you can actually, depending on this fill fraction and the wavelength, you can actually end up with different types, different domains of materials and different properties. And why they're interesting, because as you can see that this is how light propagation would in free space. But when you come to one of these materials, then you can see that the dispersion relation becomes something like this. It becomes hyperbolic, and there are two different types of the details. So if you look at this relationship, which is what will give you this one, provided epsilon, the permittivity is equal in all directions, that is epsilon zz and epsilon xx in plane and out of plane are equal, then you will get something like this. But the moment you have these two are not equal, and one is in particular negative, then you end up with hyperbola. You can see this very easily, and then that hyperbolic dispersion is what actually makes it very interesting, because you get a lot of high density of states essentially because of that. Okay, so now so a lot of study has happened with the first type. I'll start with the first type. Some examples. People have shown lasing in this type of arrays. For example, recently, more recently, there has been a demonstration of a Bose-Einstein condensation phenomena in this type of lattice, and so on and so forth. Now, these are mostly done with some sort of a dye molecule, which basically couples to the lattice mode and demonstrates this behavior. What we used in what we have been using in our group a lot are these semiconductor quantum dots, which are basically this tunable band gap semiconducting material, nanomaterials, which has this emission or absorption in the visible regime, and you can tune that regime. You can go to the IR as well, and you can see the typical spectra here, the absorption or the emission, as you see here, which corresponds to roughly this band gap. Now, we want to couple this to, so there are excitonic states which will be generated in this as a result of absorption of light, and we want to couple that to this array. In other words, couple that to this the lattice mode here, the lattice, and you can, as I said, you can get different types of depending on the spacing. Okay, so now before I come to the Polariton part or the Polaritonic part, first I will just mention briefly what you can see even when you have very isolated ones. So you see this picture here, some isolated these quantum emitters, these dots, which are sitting on the lattice at discrete locations. When you look at it spectrally, there's nothing interesting. It's boring. Basically, it's same as what you would measure, on a normal transparent substrate or even in solution. But when you look at the spectra, but when you look at something different, which is when you measure the lifetime. So these excitons, when these electrons are excited, they will come down after a certain time. So there is a lifetime they have. So when you measure that lifetime of these excited states, what you find very interestingly is that this is the data for lifetime when you measure where you don't have, it is not on the lattice, but just the isolated dots. When you measure, when you don't have the lattice mode turned on, that is, the lattice mode is turned off, but you have only the individual silver cylinder, which is giving the lattice localized plasmon resonance. You see a slight change in the lifetime, which you can see here. You can fit this to exponential function. When it is coupled to the lattice mode, you see a significant change, and you also see very clearly the emergence of two modes. So there are two modes here. You can see the bending here, and you can see these two modes. So this is just to show that these are actually single photons. So actually coupling single photons to these modes, and we basically try to model this, with a quantum mechanical model, because classical model is not going to be able to capture this decay rate. Okay, so essentially, what the message just before I go to the Polariton part, what we see essentially is that the emergence of this second rate, there are two rates. So there is the short time and a long time. The emergence of the second rate is related to the coupling between two individual dots through the cavity mode. Okay, but they're remotely located. That means they are physically not connected. However, they are able to get connected. So this gives you some idea about what possibilities one could exploit using these delocalized surface lattice resonances. So now polaritons, I mean, this is just for not for the experts, but for the more general audience. I mean, this is something which is a kind of hybrid of two different types of modes or excitations. And you can also think in terms of just two simple, coupled oscillators if you wish, and then you get the normal mode. So, basically two modes couple, and then you see here you get in the spectrum you get two upper and a lower polariton which emerges. In this case, for example, coupling excitons, as we have two photons, you get this. Okay, so there are a lot of interest these days in creating, even excitonic polaritonic lattices, and which can be, studied for a lot of applications even outside of this field. For example, using in condensed matter physics. So the first part, what we observe that when we create this, now how do we detect this modes appearing? So now if you look at this, this is what I saw, what I showed when we were looking at isolated dots. Now when you have a kind of a compact array, then what you see, and as you can increase the concentration, then you start seeing this splitting. Now the two modes which are emerging, which correspond to what I was telling, that the two modes, hybridized modes, which appear as a result of the strong coupling between the excitons and this lattice mode, and it nicely shows this behavior because it scales with the concentration. What is interesting is that when you look at this spectral feature and you look at, for example, this picture here that you excite here and you detect, so this is local excitation, but you're detecting non-local, you're detecting distance far away from the excitation, and you can still see this propagating. And this here we are able to pick up these modes, well, even 500 micron I have shown, but you can go even larger, and this is quantified here. For example, you can measure this going all the way, well beyond, 1000 microns. So it's a very, very long range over which, these modes are able to propagate, which makes it very interesting, because now you can think of creating, in an array, these long propagating one, and then you can actually try to do a lot of interesting, physics, but there's also application in terms of quantum technology and in terms of quantum communication, using some of these modes, if you can really control and design them well. So, so this was, a model using kind of a standard formalism with the Hamiltonian. This is the laser drive. This is the interaction term, and this is the Baire term. The Baire term consists of two parts: the quantum dot, the corresponding annihilation and creation operator, and this is for the lattice mode. So everything is in the quantum formulation. This represents the interaction strength, and that is what we are seeing here. So the range of propagation, what we found, is actually related to the coupling strength. So in other words, we have a handle. You tune the strength of the strong coupling. You actually can also control the range, and therefore that allows you to basically look at even possibilities of when you create, for example, a lattice. You can actually control the interaction between the lattice sides by tuning the range and this coupling parameter. So this is something that was the first part. I will now come to the second part of this, which involves photonic spin momentum locking, somewhat related to topological photonics. There has been a lot of interest in this area, where actually, to cut a long story short, people are trying different ways of having directional propagation using some parameter. For example, it could, in case of light, you could use polarization, helicity, and so on and so forth, and you could direct light. But usually in materials, what happens is that you need to have a certain, kind of a symmetry breaking. You need to have some sort of a chirality built in either into the emitting material, or for example, or the template. It has to have some sort of a, chirality, so that you then use that degree of freedom and couple, and you basically engineer the propagation. That is something that has been going on. And this has, obviously a lot of, synergy and correspondence with what is happening, for example, in the electronic field, where people have, there is a lot of interest in looking at, topological electronic materials, and especially topological insulators and so on and so forth. Okay. So of course, there you have electrons in that case, but here, in case of photons, they are fermions, and here you have boson. Now, what we looked at in this case is a system where I mentioned this metamaterial, this hyperbolic metamaterial now, and coupled to this, close packed quantum dot layer that I mentioned in the previous example. So kind of similar. And now, so you can see some of the pictures here, and when you put the quantum dot, you are not able to see. They are on the same sort of material, but it now covered with a very compact layer of this quantum dot. Okay, this kind of we know forms the type 1 hyperbolic metamaterial, and therefore it is expected to have this large density of states which basically resides on the surface. But the key thing is that if you're able to go inside the material, then you can tap this. But then on the surface, what you basically couple to are the evanescent mode. Okay, and that is very important. Now, what we see interestingly is that when you look at the the dispersion, what we find is that this. So when you come in with left and right circle, right? So you are coming in with helicity dependent. So helicity dependent excitation on this. Okay. In the previous example, it was unpolarized radiation or partially polarized. Because here I come in with this, and what I see, normally the quantum dots do not have any chirality. The metamaterial does not have any chirality. So these are completely a chiral material. But what you have is that these are now coupled, and the quantum dots are actually able to couple to in the near field of this hyperbolic metamaterial, where you can actually see these these high density but evanescent mode and high wave vector evanescent modes, right? So when you do that and when you couple, then you see that actually this is basically the wave vector and this is intensity, and then you couple with either left or right circularly polarized light, and then you can see that the left and the right circularly polarized light actually go out in different directions. So the directionality is something which is basically given by the metamaterial, which you can tune the directionality of the emission. This property of directional dependent coupling, which in a way can be thought of as an example of quantum spin Hall effect of light, is coming due to the coupling to these modes. Okay, and this is something which also was kind of borne out in detailed theoretical calculations. There is no quantum mechanics involved in the calculation. It comes because Maxwell's equations have certain properties in terms of the relativistic invariance or the properties of the photon, which actually is able to capture this. So there is per se there is nothing quantum, but it's in a way a manifestation of a quantum spin Hall effect of light. And you can see the same thing here, that depending on the helicity of the light, you see that the intensity, in other words, the direction in which light is going is also actually physically determined or coupled to the helicity of the incoming radiation. And you can see also that the chirality parameter here, for example, depends on the wave. You can see that this is actually greater than k0. And this is only possible when you have this hyperbolic metamaterial, which has a high density of states. It gives you a high wave vector states, and you can see that it is much higher when you are coupling into the high wave vector states, and increases as you can access more and more of these high wave vector states. And so this is indicated that this kind of a coupling is mediated by these high wave vector states, which becomes only accessible when you have this hyperbolic state, and not will not be available in the normal kind of circular or spherical dispersion of the system. So basically, I will then summarize by saying that that we have these two kind of aspects of this coupling that we have shown, where the quantum dots in one case coupled to the optical modes, where politrons are generated, and then these politrons can also be transported across a long distance. In the second case, if you are able to couple to these high wave vector modes, evanescent modes of this plasmonic hyperbolic metamaterial, then actually you can show the emergence of the spin and the direction and the momentum locking, which has a lot of interesting applications in various aspects, apart from the fundamental interest in this area. So I will basically end here, and thank you all for the attention, and I'll be happy to answer questions.
Usually, Polariton relates to photon and photon composite, polar phonon and photon. So in this case, when you say quantum emitters are coupling to delocalized plasmon, photonic cavity, it's a combination of plasmon and photon, is it?
Yeah, so that's an interesting point. So basically, it is the coupling of the exciton, because the quantum dots, they carry exciton. So there's exciton which is coupling to the to this lattice mode. Now this lattice mode is it's something which is generated because of the diffractive coupling of the particles. but it is not easy to basically segregate out the effect contribution of the individual particle, because that also has some contribution, and the lattice mode. But basically it is that. So you can say it is an exciton plasmon polariton if you wish. But this is essentially appearing mostly because of the coupling to the lattice mode. Yeah.
All right, thank you. There's a question from Professor Bhaskaran. He says, I hear about hyperbolic metaphonon and magnetic materials. What is the experimental status today?
So hyperbolic metamaterial actually, it's something that I think there are few groups, which are, I think, working in India. Probably globally, there is actually a lot of interest because of this, the property of the high density of states, and the area of interest is vast, because, for example, in electrical engineering, a lot of other kind of fields, you can create this in a different wavelength thing. So this, in principle, is valid in any range of electromagnetic spectrum. So you could also use other kind of regimes and materials and methods, create structures which are on maybe a larger scale, and there is a lot of interest in studying those as well. So yes, I mean, the short answer is yes.
Jaydeep, I think he means metaphonon materials, not photon. Will be probably easier to make.
So there are these also. Yeah, you're right. So there is also this acoustic metamaterials.
Right.
So that is something that is also a field which I think is also quite emergent. I am not aware of anybody probably in India who is working. We are not working on that, but yeah, definitely that field which is I think quite developing and rapidly emerging, at least globally. So there are these acoustic metamaterials as well, which are also being studied quite extensively. Yeah, thank you for the question.